Aloha, Richard Halverson here. This is ICS211. And in this video, we're going to start talking about heaps. So let me share my screen. Okay, we're going to try to cover the first three sections here of heaps. A heap is a special kind of binary tree. Some applications require fast access and removal of the maximum item of a changing set of items. Let's see, let me switch over to presentation view. A max heap is a complete binary tree that maintains a simple property that its node's key is greater than or equal to the node's children's keys. Complete binary tree means, let's see, when we talked about binary trees, we talked about a binary tree is complete if all the levels, except possibly the last level, contain all possible nodes, and all nodes in the last level are as far to the left as possible. All right, so okay, so that's what a heap is, a complete binary tree, and it has the property that for each node, the key of each node is greater than or equal to either of its children. When we insert a node into a max heap, we insert the node at the last level at the bottom, at the first place that we can put it at the bottom, and then we begin swapping the node with its parent until there aren't any max heap property violations occurring. So if the node we are adding is bigger than its parent, then it'll be swapped with its parent, and that'll keep happening as long as the node is bigger than its parent. It'll swap until the node is no longer bigger than its parent, or until the node becomes the top node. And so percolating is the term that we use when the node is being swapped with its parent to get it into the right position, so the max heap property, so there's no max heap property violation. Removing, we always remove from the top, and then we take the node at the very bottom, the last node, and put it at the top, and then we what's the term for it? It's not percolating. It is, I guess it's percolating down and percolating up. The percolate up algorithm and the percolate down algorithm. Okay, so let's go back to where we were. A min heap is like a max heap, except for it's the smallest node that's at the top. And the min heap property is that each node is less than or equal to its children nodes. So you can think of applications for this, for example, in online tech support, waiting times. You can when a person comes in, they take a number, and the number keeps increasing, and then they're added to the heap. They're added at the bottom, and as customers are pulled off the top, then the bottom one is put at the top, and then it percolates down, and then the next lowest one ends up at the top. So in this case, the 4 gets removed, and then the 21 gets put up here where the 4 is, and then it percolates down. The 21 is going to be swapped with the 16. And so you end up with this over here. All right, so let's do a challenge here. Select all the valid max heaps. Let's see, I'm going to do number 3. All right, given the max heap, when 98 is added, a new node with the key 98 is added as the right child. When 98 is added, okay, so we're going to add a second 98, basically. The new node with the key 98 is added right here as the left child of 85. So it's going to be the left child of 85. It's going to be added right there. And then 98 is percolated up, swapping with 85. So the 98 will be stuck down here right there, and then it'll be percolated up. It'll swap with the 85, and then the 98 will be here, and the 85 will be down here, and then it'll be done because it's not greater than its parent. So 98 will be sitting there, and 85 will be down here. Is this right? Yes, it is. All right. So you can do the rest of them. Okay. How do we represent heaps? Well, if you recall, it's a complete binary tree, which means it fits perfectly into a regular indexable, array, where we can index it, where we can index any element. And the way it works is, let's say we have a tree here. This is a max heap. This is the biggest. It's bigger than its 2 children. This one is bigger than its children. This one's bigger than its child. So this is a max heap. And this is how it's stored. This is index 1, or this index 0, 1, 2, 3, 4, 5. And that works real nicely with a complete binary tree because, all the spaces are filled and there's no open spaces, and it goes right to the end. And so it's actually stored in the sequential array like this: 72, 58, 63, 55, 16, 44. And this makes finding the parent and the children of the array of an element very easy, as we'll see. So the parent and child indexes for a heap. Note, this is the node index, and this is the parent. We see that the parent is the we take the index, subtract 1 from it, divide it by 2, and take the floor of that, and then to find the children indexes, you take your index, multiply it by 2, add 1. That's the left child, and then take the index, multiply by 2, and add 2, and that's the right index. That's the right child, the index of the right child. This is the algorithm for percolating up. So a node was added to the end, and then we compare while the node index is greater than 0. We look at the parent. We figure out what the parent index is by this formula right here. Take the node index, subtract 1 from it, divide it by 2. Take the integer value. That's the parent index, and then we see if the node that we're looking at, or that we're trying to percolate, is if it's less than the parent. If it's less than the parent node, then it's in its proper place. Then it doesn't need to go any further, and we simply return. Or if the node that we're trying to percolate up is greater than its parent, in other words, this is false, then we swap it with the parent. And the new index for the node becomes what the parent index was, and then we continue to loop while the node index is greater than 0. So this is the algorithm to percolate up a node that we've just added onto the tail end of the heap. This is the algorithm to percolate down. Okay, so we have removed a node from the very top, and then we take the node from the very bottom, the last node, and put it at the top, and then we have to percolate it down. Okay. And so as long as the child index that we're percolating down, as long as it's less than the array size, in other words, it's a valid index, then we're gonna percolate this thing down. This for loop simply tests both children, okay? So it tests while I goes from 0 to 1. Okay, so I goes, I is either 0 or I is equal to 1, right? So this for loop goes from I equals 0 while I is less than 2 plus I plus plus. So this is 0 and 1, but it also can be stopped if the I plus the child index is less than the array size. In other words, we're at the very end. The last node that we look at does not have a right child. Okay, so this simply ensures that we look at both children. Okay. We have we're percolating down this from this node index. The node index starts out at, would start out at 0. And we test to see if the child is greater than the value of the node that we're percolating down. If the child node is bigger than the node that we're percolating down, then the child better trade places with this node that we're percolating down, because the node we're percolating down is smaller than the child. So we have to trade places. Let's see. This resets the value of the. This is the max value. Let me see this from here. Max value is gonna figure out what the maximum value is of the node that we're percolating. This is the node we're percolating, and this is the value of the node we're percolating. So the max value begins by being set equal to the node that we're percolating down. And then what this for loop does is it figures out if either of the children, see, this I is going to be equal to 0 or 1. So this is going to be equal to either this left child, in what case when this is 0, this is the left child, and when this is 1, this is the right child. And so this looks at the value of the left child and the right child, and if either one of them is bigger than max value, then we have a new max value, and we have a new index. The index, as we're figuring out which of the 3 is the largest, if the max index is set to -1, then it's the node that's coming in. It's the value of the node we're trying to percolate. Otherwise, if it's one of the 2 children, then this max index is going to be set to that index, the index of the child that's largest. Okay, so when this for loop is done, max value is going to be the biggest, the largest of either the node or the 2 children. And if it is one of the 2 children, then max index is going to be equal to the index of that child. So here we test to see if the max value is, if the max value that we started with is still equal to the value of the node. If the max value is still equal to the value of the node, then the node that we're trying to percolate down is bigger than its 2 children. In other words, it's already in its proper place. So we don't have to do any more percolating. We're done. But if the max value is different than the value of the node that we're percolating, it's different, and that means one of the two children is bigger than this node that we're percolating, and we have to switch places with that. The node's got to switch places with that child, and that's what this does. And so now now we have a new child index, and we've got a new node index, and this loop continues until we the node that we're percolating down settles in its place. All right, so that's how you percolate down. Kind of complicated. Let's see what this does. Let's see this. Try this one. It looks like we're what is the above max heaps array form? Okay, so we're supposed to put this in what the array is. 96, 68, 93, 16, 66, 27 would be what the answer to this one is. Let's start this, and I'm going to do a more difficult one. I'm going to do this one, number 3 here. All right. Select each array that represents a valid max heap. Oh, okay. Well, this has got to be bigger than this one and this one. And this one has got to be bigger than this one and this one. And this one has got to be bigger than this one and this one. And it looks like they all are. So I would say that this is a max heap. What about this one? This one's got to be bigger than this one and this one. Oop, it's not. So that's not a max heap. This one's got to be bigger than this one. No, it's not. This one's got to be bigger than this one and this one. This one has got to be bigger than this one and this one. And this one has got to be bigger than this one and this one. So it looks like this is a max heap. Let's see if it is. Yes, very good. Okay. You can see this last section here, Java, the Java version of heaps. This just gives the Java implementation in section 20.1 and 20.2. We were just dealing in pseudocode. These are the actual Java implementations. I use the Python version of this textbook also in the Python course I teach. And the first 2 sections are the same, but then this section in the Python version of the textbook, it's got Python heaps here, but we're doing Java here. And so here is the we're defining a class called max heap. And in Java, as you know, the programmer has to manage the size of the array as the array grows. So we have this resize function, and each time we resize the array, as the array grows, as the heap grows, and the array representing the heap grows, when we hit the size of the heap, when we hit the max size of the array, we have to keep track of that. Then we double the array size, and to double the array size, we create a new array that's double the size, and then we have to copy everything over from the old array to the new array. Okay, kind of humbug, but that's how we have to do it in Java. So here, this max heap class has got a resize function, and when we initialize the max heap at the very beginning, we just say that the array size is 2, and then this resize will figure out a new length, which is going to be the current length times 2. So each time it doubles, and then we create a new array of that new size, and then we copy over everything from the old array to the new array one by one, and then we set the new array pointer, I like to call it, to we set heap array, which is what we started with. That's the array in the class or in the object that actually stores the array. That now points to this new array that we created, and we can dispense with the old one, get rid of it. And this is the Java program to percolate up. So we have just added a node onto the tail end of it, and we start with the parent. We figure out what the parent is, and we check to see if the parent is greater than if the parent is greater than the node that we're trying to percolate up, then we're done. Otherwise, we switch places with the parent. We trade places with the parent, and then we continue to percolate up. So that's the percolate up method. Percolate down method is we have put a new node at the top, and we have to percolate it down into its proper place. So this while loop here, it comes in, it sets this max value. Remember, max value figures out the bigger of the node or its two children. There's three nodes, the current node and its two children, figures out which one's the biggest. If it is the biggest, if the node itself is the biggest, max index is going to be -1 when it comes out of this loop here. Max value will be equal to the value of the node that we're trying to percolate, and then we're done, which means the node is in its proper place. It's the largest of the three. If the value of the node that we're trying to percolate down is not equal to is not the biggest, then it has to trade places with the biggest, and that's what this is right here. And then it continues to percolate down. This is inserting and removing. So inserting, it means simply we stick the new node at the end. Inserting, we stick the new node. Oh, first we have to see if adding the new node is going to be too big for the array. Adding the new node is going to be too big for the array, then we have to resize the array. Once that's done, then we can add the new node to the very end of the array and increment this, and then we percolate up. Removing a node means we pop it off the top, array of 0, pop it off the top, and then we take the very last array element and put that on the top, and then we put that on the top, and then we percolate down. So this is the heap sort program in Java. This is the demo, and this is the heap sort, or this is the max heap class. This is resizing. This is percolating up, and this is percolating down. And so, you know, and here we loaded up with this array here. Load it up. And so let's run it, see what this looks like. And this is nice. Displays out a bunch of stuff. It's interesting. We insert a 10, we insert a 2. That's at the bottom, so that's in its proper place. We insert a 5, and that's fine being a child of the 10. And then we insert 18, and that's the very end. So 18 is going to swap with 2, and then 18 is going to swap with 10, and in the end we end up with an array that looks like this. If we insert 22, we have to swap 22 and 10. Anyway, then the array looks like this, and then we remove it. So this shows a bunch of, this shows what's happening, describes what's happening as we add all the numbers to the heap, and then we remove all the numbers from the heap, it looks like. See, so here we're removing, remove the biggest one, then the next biggest, and the next biggest, and the next biggest. And each time we remove one, we have to reheap, or we have to percolate down the last one. Okay, so that's kind of interesting. Let's answer these questions here. Which requires more swaps, when the input array starts sorted or when the input array starts reverse sorted? Well, if you think about it, if array starts sorted, then it is adding elements to the heap in increasing order. And when elements are added to the heap, they're added at the tail end. So if the number that you're adding at the tail end is always going to be the biggest number in the array when it's done, then what that means is that each time you add a new number, that number has to percolate to the top. It has to percolate to the position 0, to the index 0. So if you start out with a completely sorted array and you want to sort that using a heap sort, it's going to be very time consuming because each time you add a new element, that new element gets added to the very tail end, the very bottom of the heap, and it's got to percolate up to the very top. Whereas if it's in reverse sorted order, then the number that you add at the end is always going to be the smallest one. So it's going to be added right in the place where it should be, at the very tail end of the heap. The smaller numbers tend to be at the end, and the bigger numbers tend to be at the beginning with a max heap. All right. So that's the answer to that. And how do you change the code? How do you change the code to become a min heap? A hint: ignoring variable names. Only 2 lines of code need to be changed. Well, let's see. 2 lines of code. I just well, first of all, where we percolate. Oh, probably percolating up and percolating down. So when we percolate up, when we're percolating up, we are looking for the index has got to be, the heap array at the node index has got to be, for max heap, this is less than or equal to. So when the node is less than or equal to its parent, then we're good. And that's in a max heap. It's the opposite for a min heap. With a min heap, if the node is greater than its parent, then the parent is in its proper place. The parent should be smaller. In a min heap, the farther up the heap you go to the very top, the number should be getting smaller. So I think this one has got to be less than or equal to, and that's for percolating up, and it must be like the opposite for percolating down. This one. This is going to be the child for percolating down. The child for percolating down, the child should be, if the child is smaller, then it is not in its right place. The child should be bigger. So that means this should be less than instead of greater than. Yes, less than. So if the child is less than, then we want to remember that, because we need to trade places with that child, because the smaller one should be at the top. For a min heap, the smaller one should be at the top. Really, do you notice it says ignore the variable name just because we really should call this min value, min index, and min value, and so on. But we're not. We're only changing this, the greater than to a less than, and a less than or equal to a greater than or equal to. I think that's right. All right, let's see what. Let's run it again. So I guess this is a min heap. So we're going to remove the 2, and then the 5, and then the 10, and then the 18, and the 22. So that's sorted in ascending order. All right. Well, anyway, that takes care of sections 1, 2, and 3 in talking about heaps. In the next video, we're gonna go into heap sort. We're gonna talk about heap sort, and then after that, we'll be ready to do our lab number 5, I believe. Yes. Anyway, hope this helps. Thanks for watching.